All right, let's take a look at question 23. In question 22, we looked at how to solve systems of linear equations. In question 23, we have a system of exponential functions or equations that we want to solve. Okay? Question 23 reads, materials A and B decay over time. So we have exponential decay here. The function for the amount of materials A is A of t equals 1000 times 0.05 raised to the 2t. And for the amount of material B is B of t equals 1000 times 0.25 to the t, where t represents time in days. On which day will the amount of material be equal? Okay? So when we're looking for the day when the amount of materials are equal, what we're looking for is the intersection of these two functions that we have right here. Okay? Alright, so let's go ahead and write down what we are going to do. So the time when amounts are equal is when A of t is equal to B of t. Okay? So basically, if we want to do this graphically, what does this mean graphically? Graphically, we find the point or points of intersection. Alright? Where do these two graphs intersect? Wherever they intersect, those are the times when the amounts are equal. Okay? So what we're going to do is we're going to graph these two functions, and we're going to see what the point of intersection or points of intersections are, and then that will be our final answer. Okay? Alright, so for the first one, we have 1000 parenthesis 0.5 raised to the 2t power, so just use caret 2t parenthesis 2t. Since you have 2 and t in your exponents spot, we want to put parentheses so we do not have grouping errors. Okay, so as you can see in this button right here, that button represents x, t, theta, and n. So when you're graphing, it's a function of x, so the x is what is used in place of t when entering it into the calculator. Alright, x and t are your independent variables, and they are interchangeable. Alright, so for the second equation, we have 1000 parentheses 0.25 raised to the t power. So t in this context is just x. Enter. Alright, so we want to look for the intersection of the two. So let's do a standard zoom. Zoom 6. So here goes the first one. And where is the second one? Where is the second graph? We had the first one, and it looks like the second one is either the same as the first one or somewhere else. So if you have a situation like this, one thing you can do is you could do this. So what I want to do is I want to show an animation. I want to show a pathway that the graphs followed. Okay, so just in case we have an overlap. So here, instead of line, I'm gonna press enter, 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 enter. So it's gonna show a ball, a little circle sweeping the path of the graph. And then here, the same thing. Instead of just a line, it will be a line and a circle showing the pathway that the line passes through. All right, let's graph it again. So check this out. So you're gonna see that right there. So that's the first one. You see where the first one is, and then the second one is exactly on top of the first one. They are one and the same. Another way you can look at this to see that they are actually the same graph is to consult the numerical representation. Just go to the table, and what you notice is that y1 and y2 are always the same. Always the same. So how many times do they intersect if they're always the same? They intersect at every point in time. You have infinitely many solutions. Okay, so let's go back to the question. For what days? For all days. Okay, since we have infinitely many intersections for all days, the quantities are the same, or the amounts are the same. So the answer to question 23 is option 4, because we have infinite number of intersections. They are actually the same function. Okay, so that's that. All right.